aí. Olha só. Me pede desculpa porque está tão clarinho aí, né? Mas se vocês puderem chegar mais para frente, talvez possam enxergar melhor, né? Então eu queria apresentar aqui, para quem está assistindo o curso de Londres, que essa aula está dividida em duas partes, como a gente faz de vez em quando, né? A primeira parte vai ser o seminário, e a segunda parte a gente depois se aguentar, né? Vamos ver até que hora vai o seminário, então aí a gente faz a aula, né? So, Luca will speak in English, so I would like to acknowledge Luca so much, for the visit, for all the discussions we have had with Luis. Luis also participated in this collaboration, and Luca very kindly offered himself to give a talk. We are not paying him, he's paid by France. He has the budget jet from France to visit Brazil, so he has been here for 3 weeks, almost no.
Yes.
This is his second visit, he comes here this year. He's doing his PhD at the University d'Orléans under the supervision of Alessandro Spalletti, colleague of ours from Italy, but he's professor in France. And so, Luca is collaborating with Professor Santiago Berliafa at UERJ, and your collaboration is just the seminar today. No, exactly. I am not involved in this work. My name is there just as a collaborator, but another collaboration that we have with Luis, Luca, and Alessandro. Alessandro basically today is going to speak about the works he's doing with Alessandro, Luca, and Santiago. Okay, so some aspects of nonlinear versions of 3D. Okay, so thank you so much.
You're welcome.
And we hope to enjoy your talk.
Bom dia, and that sounds like Portuguese, so don't expect more. So, as I said, my name is Luca Bonetti, and I'm here today to talk to you about electromagnetic shift in the Euler-Heisenberg theory and radiation for a Born-Infant accelerated particle. My work is funded by the University of Orléans and by the French CNRS, and my supervisor is Alessandro Spalletti, and like I said, this work has been done in collaboration with Santiago Berliafa. Here is a brief outline of the presentation I'm about to give. First of all, I will introduce a little bit the electromagnetic context. Then I will discuss nonlinear electromagnetic theories, pointing out 2 different classes: the classical nonlinearities and the quantum nonlinearities. After that, I will go to what is more directly my work, which is the Euler-Heisenberg dipole, in which I will deal with effective metric formalism, that is the context in which we have worked to obtain our results. And then I will discuss how we got the shift, and I will present some results. The last part is still a work in progress. It deals with an accelerating particle inside the Born-Infant context. I will speak about the problems of calculating such fields for nonlinear theories. Our context is the one of linear spacetime, so I will speak a little bit about linear spacetime, and then I will show how we approach the problem. And then there will be some conclusions. Okay, I must apologize for these 2 slides because I know that all of you know about electromagnetism, but I wanted to put them here anyway to compare and contrast with what will follow. So, of course, we know that the electromagnetic phenomena are described by a very well-known theory, Maxwell's theory. Maxwell in 1864 summarized a couple centuries of experiments in this very famous equation, the Maxwell's equation. Now, of course, this theory is linear, and it can be derived from a Lagrangian through the extension principle. The Lagrangian is here. It's written in terms of the usual Maxwell tensor, which is written in terms of the for potential, which is linked to the usual physical potential by these relations. Of course, we know that from quantum standpoint, the field A mu is linked to a particle, the photon, which is massless. And we also know that electromagnetic theory works very well, as it has been proven in the last couple of centuries, but there is still room for improvement. Namely, there are still some limitations. In fact, the superposition principle is a principle and therefore can only be checked experimentally with a certain precision. Also, the masslessness of a photon can be only checked up to a certain degree of precision. But maybe more importantly, when we want to pass to the quantum context, the transition is not straightforward. In fact, to pass to QED, we need instruments like renormalization that are quite artificial. So there is room for nonlinear theories. Nonlinear theories, there could be a lot of things to say about non-Maxwellian theories. Today we will focus on nonlinear theories because, of course, the two main classes are those the theory in which the photon is massive and the theories in which the particle that is beyond Maxwell's is coming from nonlinearities. We will focus on this one today. Like I said in the outline, there are two
nonlinearity of what? Of the electromagnetic field, the photon?
Of the Lagrange, normally. The electromagnetic fields come in the Lagrange in a non-linear way.
So let's say you preserve Maxwell Lagrangian and make nonlinear terms.
Exactly.
Just that.
Exactly.
And let's say this is the only one way to do nonlinearity.
It's the only one way. It's the most simple, let's say. It's because we know that Maxwellian electromagnetism works very well. So basically, what we expect is that even in regimes where Maxwell theory breaks down, we should have very tiny effects added to what is the Maxwellian part. Therefore, and more importantly, in the limit, the classical limit, so to speak, the additional part should vanish because we should recover Maxwell expressions. Therefore, the most logical and simple way is to add terms. But for example, Euler-Heisenberg theory actually is a force of correction, like I said, and it can be used separately from there is the Maxwellian part, and then you correct the correction of the Euler. I don't know if I'm trying to your question.
No, I would like to listen to you because what I'd like you are going to give your seminar, but always explain for us what does it mean for you the electric charge. Maxwell, who have one conservation law for electric charge. Electric charge is the source of electromagnetic field. What's the difference?
Okay. The conservation of charge, all the fundamental symmetries are older. They are older. We don't break gauge symmetry or this kind of stuff. We simply add nonlinear terms. Okay.
But I think when you add nonlinear terms, if you need you introduce new charges, what are the new aspects of one you should just change the equation of motion, or you change it in some aspects in physics?
Usually it changes the equation of motion. We don't add new equation of freedom, if it's that question. Like I was saying, the nonlinearities can be present at classical level, or they can arise only in the quantum context. I will show for the first class the Bonetti theory, and for the second class the Euler-Heisenberg theory. Okay, classical nonlinearities. What is the current status as far as experiments go? The linearity representation principle has been proven at macroscopic level with 0.1% precision, namely with transformers, diffraction pattern, X-ray crystallography, and reflection. But of course, the most probing test must come from atomic and nuclear physics, because it's there that when we go near the localized charges, the fields reach strength such that it is possible to break Maxwell theory. Therefore, people investigated also these regimes, and for fields up to 10 to the 15 volt per centimeter, which is inside the atoms, thanks to the energy level distances, we have proven that linearity is actually acceptable with a precision of 1 part in a million. The same precision has been reached inside the nuclei with fields of the order 10 to the 19th volt per centimeter.
So just again, let's say you are not speaking about the photon, no?
Right now, this is classical. So in the classical theory, we don't speak of photons. This is purely classical electromagnetic fields, and when we will deal with polarized theory, of course we will talk about photons, because that's quantum. The constraints are very restrained, but there are still room for improvement. In fact, we know that there is a feature in classical electrodynamics that is very strange. The electron self-energy is infinite, and this is something that is very strange. Therefore, in 1934, Born and Infeld came up with a theory that in principle should solve this problem, the Maxwellian theory. Theory based on 3 principles. The principle of finiteness, that means that all physical quantities inside the theory must be finite. This doesn't mean that everything inside the theory is finite, but everything that we can measure of the theory must be finite. The second principle that they use is parallel with relativity. In fact, before Einstein's revolution, the speed of light was not bounded from both. Instead, likewise, in the Maxwell theory, the field of the particle is not bounded from above. So the idea of Born-Infeld is, can we reproduce what Einstein did for the motion of the particle, for a charge, for a field? And the third principle, which nowadays we disagree upon, but I put it here anyway for historical reason, is that they believed in what is called a unitary vision of the world. For them, the only physical entity was the electromagnetic field, and charges were simply singularities of the field, and the massive particles, was just an expression, a concept that was a derivation of the electromagnetic field. And in fact, they talk about electromagnetic mass. If you want, sometimes there are the references at the bottom of the slide. Okay, like I was saying, they were trying to mimic what Einstein did. Here we have the kinetic term for a classical particle, and here we have the kinetic term for a relativistic particle. And we see that C is an operator. So what they did is exactly the same. They took Maxwell's structure and they written that in a form which insert in a parameter that bounds the fields from above. If the electric field, for example, exceeds the value of B, then the square root becomes imaginary, and we have theory breaks down. Okay, these are the usual notation that in every text. Of course, if we know that F can be written in terms of the field like this, and G can be written in the term of field like this. So if we go back to this expression, this term here is of the 4th order, and this in the fields, and this term here is the second order in the fields. Therefore, usually the Bonetti Lagrangian is simplified into this form, disregarding the part that depends on G. By the least action principle, we can derive the equation of motion, that are these one here, and also this 0, 1 here is the other couple. These being purely geometrical do not change, with instead these being actually containing the dynamic of the particle do change. If we write the equation of motion in terms of the field, we obtain this form here. I believe this slide is a little bit difficult to see, but you can appreciate that formally they are absolutely identical to Maxwell's equation, but for two particularities. Here appears the field D, not the field E, and here appears the field H, not the field E. The positive relation between the field D and the field E and the field H and the field B is given here. And from these two denominators, I don't know if you see, but they are equal. So what happens is that we can interpret vacuum like a nonlinear medium which has magnetic susceptibility and the electric constant equal to this fraction.
Yes, just a question. Yeah. The thing was Maxwell's equation does not describe the polarization of the station. So they are introduced by hand.
Yes, exactly.
Okay. You are saying that for here we could say that the polarization and magnetization are introduced by first principles.
No. If you have, let's say, a medium which is non-trivial, okay, you must add that magnetization and polarization by hand still. Okay. If I wrote this equation here in terms of E and B, of course they would change with respect to Maxwell's equation. What I'm saying is that I can write formally the equation as if it were Maxwell, just changing the field that I use.
So, but you are not. If he, for instance, if you read your, I'm not being able to read so much because I'm saying I'm trying to understand what's polarization and magnetization. Because just one question: if it is one granular effect or it is one collective effect. Reading your equations, we can have some clue that it is an effective, collective aspect in the electromagnetism. Because you wrote the E, the displacement. You are now with a constitutive equation.
Yes.
Yes. Inside.
We do have a constitutive equation. We have two constitutive equations actually. But the point is that they are not physical. I mean, the vacuum stays vacuum. It's not that the vacuum acquires a polarization or a magnetization. It's simply the way we write the equation to deal with it that changes. The vacuum stays vacuum. Okay? Exactly. It's a way of rewriting the equation in a form that is close to Maxwell's one, so that we can actually use the same result that we have in Maxwell theory, and then simply imply the constitutive relation to obtain the field in Bonetti. Because we have a great deal of literature for this equation here. So, if we are interested in understanding what the electrodynamics for Bonetti is, we can simply refer to the literature that we have, and then when we have the solution for D, we simply that is not so simple, but in principle, we simply invert this constitutive relation, and we obtain the solution for D. Okay?
So, you are not with the idea to give the first principle?
No.
Exactly.
At the beginning, I told you that the Bonetti theory implies that there are no physical singularities, and this is precisely what I meant. If the E field is never singular, the unphysical field D can be singular, but the field E stays always finite. Let's take, for example, the electrostatic and time-independent case. Then we have this equation. If we have spherical symmetry, we can perform the integration like this, and we obtain this form for the field D. Of course, we can write the potential for associated to it, where R0 is usually the usual classical electron radius for the electron, and the function f is defined by this expression here. With some algebra, we can reshuffle the function into this form here, where this is an algebraical function, and we obtain that the potential phi at 0 is given by this numerical factor times E divided by the classical radius of the electron. This means that this expression here is finite, and this is the expression for the field, the potential associated to the field E. Okay. The electrons are seen as discontinuities in the E field, and they have finite energy because of that. This theory here, this is a very important characteristic of Warning theory, is the only nonlinear theory that does not imply birefringence. Other more subtle things is that Warning theory imply metastable orbits for Coulomb potential scattering, and it can be derived from a string theory in equal form. Let's come now.
Let's say, here you can say that you are bringing a new special relation.
Yes.
And could you tell for us what does mean for you? What are the implications? Experimental implications.
You mean with the Coulomb scattering here? You mean?
Yeah, the Coulomb, and then also with the new dispersion relation that you have. No?
Where is the new dispersion relation? Sorry.
No problem. I was reading the grid represents something indirect.
Birefringence? It does not have birefringence.
Huh?
It does not have birefringence. It does not. It's the only nonlinear theory that does not have birefringence.
So let me see if I understand. You throw the singularity that's in the field to the physical field D.
Yes.
Okay, but electron has mass. So you meet some discontinuity in the field. In this is the mass.
Exactly.
Not in field energy.
Yes.
Something like this.
Exactly.
Okay, but the field in the point where is the electron? It's not talking. It's discontinuous. It's continuous. You have some not punctual. Point-like character. It's something like posso dizer espalhado. Scattered.
I'm sorry.
At the point, at the origin, what have this? What have that? What's the field in the origin itself? In the point 0.
The point 0, the field is given by this expression. By the derivative of this expression.
Okay. It's not infinite.
It's not infinite. It's not infinite. It is continuous. If you come from one side and then from the other, it's discontinuous because, like you said,
because the mass.
Because of the mass. But it's not. I mean, it's discontinuous, but it's not infinite. It doesn't diverge. Okay. Like I said, the electron mass can be interpreted like the discontinuity in the E field. Okay. Okay. Let's come out with the quantum nonlinearities. In the quantum context, we have plenty of evidences that there are nonlinearities because QED has nonlinear effect all the time. Basically, it can be deduced from the fact that we have uncertainty principle, and for a short amount of time, we can violate energy conservation. Therefore, we can have a creation and annihilation of virtual electron positrons, and this phenomenon is known as light-light scattering. if you wanted to have a comparison with a classical wave, it would be like having two waves coming in and with two wave vector K1 and K2 and going out with two different vector K3 and K4.
Sorry, you can have light scattering at 3 level?
No, you cannot have light scattering at 3 level. You must go beyond 3 level to get light scattering. Like something in this case, something like what has been done in the world.
Just to level. So no of these models, they do not have light scattered level.
No, it's only because all this theory, all these let's say quantum theory, theories that have nonlinearities that produce quantum effects actually can be seen like effective theories that mimic quantum effects from a classical Lagrange. Okay.
Yeah, as physicists, how do you support one idea that you are studying on the scattering that at 3 level it doesn't have what it has one loop?
I'm sorry, I didn't understand the question.
I'm asking you, let's say you were a medical doctor, a physicist.
Yes.
And I would like to make a question. You make one experiment with light scattering. Okay, it exists. Then you say, oh, I have one model, but at 3 level, it doesn't exist. The final graph. But just one loop.
Yeah, exactly.
Then I'm saying, okay, but if your theory has a physics background, it should have a 3 level also. One loop is just a correction from 3 level.
Yes, but it doesn't. I mean, the correction can give you new physics. It's not necessarily that all your physics is inside your 3 level.
Yeah, this is one perspective.
I mean, it's like when you perform in classical physics a Taylor expansion. Okay, if you stop at second order, you of course cut off some effort. If you suppose that you cannot solve a problem analytically, okay, and you decide to make an approximation and stop at second order in a certain Taylor approximation. Cutting the series, of course, you cut out certain effect. Okay? Like I was saying, something similar to what has been done in Bonetti can be done also in Euler-Heisenberg theory. That is, this light scattering can be interpreted as a property of the vacuum. We can imagine the vacuum as a certain magnetic and permeability and electric polarization, which induce the light scattering. Therefore, we can write our field B, like in usual electrodynamics, medium electrodynamics, like a sound where a certain tensor multiplied by the vector E, and the same for H. And in 1934, 35, Euler and Kochen derived the expression for these two tensors here at first order for slow varying field, low frequency field. The same result has been generalized by Acker for fast varying fields. And basically, what Euler-Heisenberg theory is nothing more than the generalization of what I just said. Euler and Kochen result is just the first order, whereas Euler-Heisenberg Lagrangian gives a closed form for all orders of the for these tensors. Now you will have a lot of trouble to see this this thing here. But okay, this is the Lagrangian for Euler Heisenberg. This first term here is over the alpha. It is alpha, the fine structure constant, and
but rather not follow what it said.
and this means that this is a correction to actually the Maxwell element. And this term here is the critical electric field, which is the value of the electric field above which the Dirac electrons tunnel into continuum, giving rise to an electron-positron pair. In more modern terms, that is the Schwinger field, critical field, which is the threshold above which non-linear QED becomes relevant. Of course, to the electric field corresponds a magnetic critical field, which is the field strength needed for the associated energy of a cyclotron pulsation for an electron to be equal to its mass. And I give the value because this is will be important for us later on. And the value is the order of 10 to 10 Gauss. If we expand this Lagrangian to quartic order in the fields, we obtain orthogonal results like usual, like we expected. Of course, the effect of particle creation and annihilation can be seen like a tunneling from the Dirac to the continuum, and with this Lagrangian, the correct tunneling rate has been computed and is given here. This is an important remark because Euler Heisenberg theory actually has been computed in the presence of a vector field, of a fixed, of a constant vector field. But Yun showed in this work that through a derivative expansion, this theory can be used also when the background field is not constant. And another technicality is that this Lagrangian is right for the soft Fortin regime. This expression here is a rewriting of the original Lagrangian in a more appealing form because actually this thing here can be integrated with numerical methods and gives results up to the third and fourth order. Okay. Euler Heisenberg theory is not just a cute effective theory, but it is being used right now. There are two European experiments, one is the class, the Italian one, and BMV, the French one, which are trying to see that a laser beam is actually deflected by a much more concentrated pulse. And this is an effect that has been predicted by the Euler Heisenberg theory and should be visible above 100 petabytes. This theory here has differentials, as we will see later on, and it also allows photon splitting. And I saw that here there are a lot of quantum field theory physicists, or you will be happy to see that it has been generalized for non-abelian fields and has been used in gluon to study gluon fields. Last but not least, it can turn out to be useful when we want to investigate gauge theories on curved space-time, and it has been used to study the particle production on cosmological distances.
Here, LHC also can be.
In principle, yes. As far as I'm aware of, there are no experimental data at LHC, but in principle, yes, it could be useful.
About the photon, there's some words more that you can match, of course, but which word is more we could listen about the photon behavior. For instance, it can have one speed bigger than c.
No. No. The finiteness of the speed of light is possible. What is actually there is that photons travel with at the speed of light, but what is actually true is that they do not follow the background geodesics, because actually the nonlinearity of the theory accelerates the fields. No, it doesn't change the speed, but it changes the direction. It changes the geodesic that the photon follows. And this will be part of actually what we will show with our results.
So that you have a nonlinear photon equation,
Nonlinear theory, yes.
a photon equation, but the speed
Light
is remaining.
It's always changing. It propagates at velocity c, but it doesn't follow the geodesic of the background. Because there is the nonlinearity of the theory that acts on the photon and changes the geodesic. Okay. Now we come to actually what has been my work, our work, and there have been several attempts to measure deviation from Maxwell theory that are according to Euler-Heisenberg theory on terrestrial level. The most famous one are the search for the Finger effect, the vacuum with efficiency, and the photon speed. But there are astrophysical contexts inside which we naturally have sources endowed with a magnetic field that are the ones that we are actually looking for. For example, the newly found magnetars have fields that are up to 100 in the critical field. And therefore, one could ask if they can be used to test Euler-Heisenberg theory. Actually, some work has already been done. In fact, many people studied the optical property of vacuum under the influence of such strong fields. Many people studied the polarization of phase lag, and even more people studied how the quantum vacuum friction affects the spin time of pulsars. What we wanted to do was to inspect light propagation, photon propagation under these circumstances, and we calculated the redshift associated, blue shift associated to these nonlinearities. Of course, we cannot tackle immediately the problem of the magnetar because it's a hugely complicated object. Therefore, for the time being, we stuck with a toy model that is simply a Z-directed dipole inside endowed with the overtaker. Okay. Effective metric. The formal reason we said we work is the effective metric one. Basically, what has been proven by Novello and others is that high energy excitation of nonlinear theories, they propagate not in the background metric, but in an effective metric that depends on the background metric itself, on the background electromagnetic field configuration, and of course on the details of the nonlinear theory. So basically, what happens if we take a certain field propagating and we choose a certain characteristic surface for that field propagating, we can assume that the field is constant on the characteristic surface, but its derivative is not, and therefore we define this discontinuity tensor. This is a method that is very old. It's been proposed by Adamar already at the beginning of the century. Now let's take a Lagrangian depending on two parameters like f and g, which is the case of the Euler-Heisenberg theory. The equation of motion are given by this equation here, that is not surprising, of course, and where, of course, this symbolism is being adopted. Thanks to these formulas here, we can assume that the dynamics of the particle is given by this equation, which, with opportune contraction, gives this form here, where we have that this is the usual term here in the propagation equation, and this term here depends on the effective. So everything relies on calculating this effective metric. With some algebra, I can prove that actually this effective metric here depends on the solution to this equation, this second order equation, where the parameters are written here, but for the purpose of this seminar, they are not relevant. The solution to this equation is given here, of course, it's not surprising, and for your question, from this expression here, you can see that the Bonetti theory does not have Eurythmius, because if you put this coefficient here inside here and use for L the Bonetti Lagrangian, you actually obtain that delta is 0. I haven't shown it here because it was not the point of my talk, but if you do, here you obtain 0, and of course you have only one solution from here. Instead, here we have two solution parameters if the Lagrangian is more general, and therefore the effective metric actually is twofold metric, one for the plus and one for the minus sign, and is generally given here. Of course, we can take only the linear part, and we can apply the economic approximation, and therefore we obtain the simplified version of the former two metrics, where the 0 means that all the quantities must be computed at the level. Here comes the part regarding the computation of the electromagnetic shift for a photon, which must be taken into care, because like I was saying, professor here, what actually happens is that the nonlinearities accelerate the photon, and therefore they do not move on the background velocity. The equation of motion for the photon is given by this equation here, where the covariant this is the normal equation of motion, but for this theorem, meaning that the covariant derivative has been taken with respect, has been constructed with the effective metric, not with the background metric. So we can define this other quantity exploiting a Killing vector of the background metric and hence of the effective metric. And this quantity here is of course conserved along the work. If we specify in the Minkowski framework this vector field, this Killing vector here, we can write, we can inverse this relation, obtain A0 in terms of P tilde. And by definition of the redshift, we obtain this formula. Now, we know that the zero component of the force velocity, as is here, is followed from relativity, inserting everything inside this, we obtain the relation here, which with some more algebra reduces to this expression. And this is actually part of our work, because there has been some articles published in which people naively use the usual form with the square root here. But actually this is not correct. We have put forward this correction.
So Luca, and you actually get a redshift or you can get a blue shift?
We get both. Depending on the polarization, we get once redshift, once a blue shift.
I see. And I don't know if you have been interested in this question, but could you come back to the previous slide, please? Has someone classified, given the effective metric constructed upon the electromagnetic field, has anyone classified Killing vectors to see the symmetries, the effective isometries of this metric?
There has not been a comprehensive work, at the best of my knowledge, of course. What I know that has been done, for what I can give you the reference afterward, for specific choices of the Lagrangian, there has been the study of the effective metric that Novello, for example, did some work on this. But there has not been a comprehensive mathematical study of how this equation here, there has not been a comprehensive mathematical work to study this equation in terms of mathematics. Let's take a general G tilde and study this equation here. Let's see what the Killing vector for this metric are. And then from that, let's infer something on the electrodynamical property.
Yeah.
That has not been done, to the best of my knowledge.
Okay, thank you.
Okay, so we can use the GT that we have presently computed, this one, and we obtain this simple result. That would be our redshift. Now, for the case of an exam, we have a pure z-axis directed dipole, which means that we can take G equal to 0 because we have no electric field, and that F are reduced to the square of H2. For this particular configuration, the derivatives of the Euler-Heisenberg Lagrangian are given, namely by Landin, for what we are regarding. Introducing this new variable psi, B over the critical, the derivative of taking this one here. This one is, I don't know if you can read, but this is the derivative with respect to F, and this is the second derivative with respect to G.
Luca, may I ask a question? It's on the physical scenario. So I understand that you would like to consider dipoles. You are talking about magnetic dipoles.
Yes.
Because you have mine, for example, magnetic cars or some neutron star, pulsar is a very huge magnetic field. Now, so okay, it's okay for me. Now, why? I mean, when you say Euler-Heisenberg, you are saying Euler-Heisenberg in the sense that you have Euler-Heisenberg like if4 terms and before terms, or you have even the coefficients given by Euler and Heisenberg?
No, also the coefficients.
So the quantum coefficients calculated that one loop into it.
It's precisely Euler-Heisenberg with all the coefficients that they should be. Simply, of course, these expression here, they are not exact. They are computed in the high energy regime. Because, of course, you can Euler-Heisenberg Lagrangian, you know very well, it's not trivial, so you cannot make an analytic derivation of the Lagrangian. But if you take the limit either for small energy or for big energy, you have analytical. You don't have analytical expression. You have series expansion, and the series expansion you can derive.
So,
and
but
you think this.
So, but when you are doing that, so you already, let us say, you already know, or you already is imposing that your magnetic field is larger than some critical value. Let's say it's larger than the Schwinger value.
Yes.
So, and you have, let us say, this information from astrophysics. You know that the magnetic fields are of the order of 10 to 8, 10 to 9 Tesla.
The point is that from astrophysics we know, like I said before, that magnetar fields that range between the critical magnetic field to 100 magnetic field.
Okay.
So we are interested in the overcritical region.
Because so this is when Euler-Heisenberg will give good contributions, sensible contributions. You know?
Actually, there is another paper written by don't remember, but I can give you the reference. In this case, actually both limits, the high energy regime and the small energy regime. Because actually, of course, the correction must be there at all for all regimes. Of course, it's visible more relevant in the high energy regime because of how the theory is constructed.
Okay, it's clear to me. Thank you.
So, like I was saying, we have a z-axis direct dipole. So, the potential is given by the usual dipole potential, and the background magnetic field is simply minus the gradient of the potential. And because, like I pointed out before, Euler-Heisenberg correction is already order alpha, we can simply, we are satisfied with the zero order inside the calculation. Now we introduce this parameter lambda just for simplicity because actually here depends on the magnetization of the radius of the magnet. If we think about the magnetar, this is the magnetization of the magnetar, this is the radius of the magnetar, which actually we do not know exactly, so we hide all this inside the parameter that we choose according to. And we and that we decide our variable, of course, from this here, this. And here I present some results. What do we have here? On the left-hand side, we have the redshift in terms of the field for the first polarization. And on the right-hand side, sorry, we have the redshift in terms of the field for the second polarization. We see that the effect is more in both cases, but we have two different. Of course, the redshift grows with the field in both cases. It's must be noted that this is negative. This is negative. So this is a true redshift, and this is a point, so this is a blue shift. And this redshift here grows much more steeply. And this is because, I forgot, sorry, the LGG has a divergent curve here. This is a proportional to C, so when C goes to infinity, this explodes. And that's because of this very fast growing term, we see that this redshift here grows much more steeply with respect to the other one. And also the order of magnitude is different because here we are 10 to the minus 4 and this is 10 to the minus 2. So there are two orders of magnitude. In this slide here, I present always the redshift, but in terms of the angle. And they have been computed for 3 suitable values of the parameter lambda. Because of what I said, that the magnetic field of the magnetar varies between 1 critical field and 100 critical fields, the lambda parameter ranges between more or less 1 and 100. So we took the 3. We see that in an absolute value, the redshift grows with the angle. But, of course, for this polarization here, being a redshift, we have a maximum at the equator and a minimum at the poles. For this polarization here, instead, we have a minimum at the equator and a maximum at the poles. We see that with the intense, the effect becomes more and more intense the more the parameter lambda grows. That is, the more intense the field is, so to speak, the more intense the redshift is, which is actually what we expect. Okay, this is essentially what I've already said. This is an interesting consideration that is, if we take, for example, some imaginary values, but they are sort of physical for a magnetar, we have two solar masses and 10 kilometer radius, we would have a gravitational redshift of the order of 0.2. So if we go back here, we see that the effect for this polarization here is actually comparable with the gravitational redshift. This polarization here, because it grows less steeply, is a little bit, it's a couple order of magnitude underneath the gravitational redshift, but it still can be measured within the accuracy of today's telescopes. Another interesting feature is that this is actually the first step in our work. What we aim to do is actually to create a toy model, a more complicated toy model for a magnetar, and the first next step would be to add rotation to the dipole, and we expect the effect to be increased by the dipole. These results has been been submitted to classical quantum gravity and implemented the mass spectroscopy.
Luca, you not finished afterwards I asked. Let
No,
me
no,
finish your results. This is another stuff.
About the horizontal theories, I start with the...
So, if you, I mean, do you have today dates at your disposal that makes you to know whether you are measuring a gravitational or an electromagnetic redshift?
No.
There's no way to
This is the key problem actually.
Mm-hmm.
Because this is what we discussed the other day. There are no independent ways to measure the frequency at which the photon is emitted.
Mm-hmm.
If we knew the frequency at which the star emits,
mm-hmm.
we could, in principle, distinguish between gravitational and electromagnetic shift. But unfortunately, the only sources that for which we know what is the emitting frequency are the supernova, A1 supernova. But for those we do not have this effect. The fields are not strong enough. The magnetic fields are not strong enough to actually have measurement of.
So there it's dominated by the gravitational redshift.
Yeah, exactly. In supernova, the gravitational field is so strong that actually all the other things will be lost within the accuracy that they have.
Okay, thank you.
Okay, enough about Heisenberg. Let's talk about one a little bit. Of course, in Maxwell theory, we know the field of an accelerating particle, and we also know that it's not surprising because the field is singular at the origin. The field is singular when we try to compute it at the point where the particle is. But we have seen that Bonetti theory smoothes this singularity, and therefore we expect the field to be actually regular everywhere. That's why we came up with the idea to compute it. And the reason why nobody managed to do that is that simply the nonlinearity theory makes it impossible to solve the equation analytically. Let's remind how the field is computed in Maxwell. Of course, we compute the linear Vickers potential, and then by differentiation we obtain the field. But how are the linear Vickers potential computed? Well, they are computed with the Green function. But what is the Green function? The Green function is the impulse response of an inhomogeneous differential operator on a certain plane and given a certain boundary dimension. But the function, the response to a certain function is obtained by convoluting by superposition the function itself with the given function. If the theory is nonlinear, we lose this chance here, and that's why we cannot imply common inputs to compute coordinate fields. However, the problem can be tackled otherwise. That's our ideas. Of course, we could try and compute the field in an inertial frame, but why don't we try instead to put ourselves in a non-inertial co-moving frame with the particle, compute the field in that frame, the reference frame, and then come back to the inertial frame? Well, this is not for sure not an approach, and in fact, this is the idea that in the gravitational context has been attributed to Ringler. In fact, we chose to work in a linear space. I don't know if you're familiar with, so let me revise a little bit what linear space is. So basically, that we can choose a non-linear coordinate transformation that maps this wedge here, the section inside this wedge here, such that particles accelerating on the x-axis move along this hyperbole here.
So you have constant acceleration.
Constant acceleration, yes. Actually, Ringler formula can be generalized for non-constant.
Yes.
But in our case, we stick to constant acceleration. Just for being complete, for sake of completeness, let me say that the Ringler spacetime covers only one wedge of the inelastic spacetime. But actually, with sign modification of the transformation, we can cover the whole spacetime. Here we have particle accelerating on the right-hand side of the x-axis. In the anti-Ringler, we have particle acceleration in the left-hand side direction of the x-axis. And this wedge here is called the mean wedge, and is physically represented by a bundle of particles all passing at the origin at time 0. And with different velocities and moving, let's say, outward from the origin. And this wedge here is called anti-mean, and it's actually represented by a bundle of particles coming from the past to the origin and passing through the origin at time 0 with different velocities. The problem, like I said, is that the price that we have to pay in order to pass to the co-moving frame is that the coordinates are not linear anymore, because of course we must carry resemblance of the fact that the particle is accelerating. Therefore, we must use the GR expression for Maxwell equation, which is here. Now, in the Maxwell context, this problem has been solved. If you choose, for example, this form here for the linear spacetime, we have that this is expressed in the Cartesian coordinates, but these two coordinates here are actually only an angular part, because the problem has actual axial symmetry. So in cylindrical coordinates, the fields can be written like this, where the denominator is here. And rho, like I said, is simply the radius around the y-axis.
This associated to this metric, is there any curvature?
There is no curvature, but you must use GR technique to deal with it.
No, I understand. Okay, because you have a non-trivial connection, but you don't have curvature. I see. Okay, that's what
So, basically what people have done, like Butte, Parmanaban, everybody, they computed the fields and then went back to Maxwell, to the inertial frame and obtained the field in Maxwell. That's good. But we want to do the same thing within the nonlinear framework. In that case, the equation we need to solve is not this one here. It's the same with the additional nonlinear third part coming from the Born-Infeld range. Unfortunately, this term here depends on the modulus of the field squared depth. So this is highly nonlinear, and therefore it's not trivial to deal with this equation. This is how we wanted to approach the problem, basically. We take, as just for the sake of simplicity, this redefinition of the fields is simply the usual field multiplied by the square root of the first term in the metric. With this definition, we can write the Maxwell's equation for the inverse space-time, which is like this. And by the first one, we know that all these things inside here must be the gradient of a certain potential, which is what I like to write here. And the field, of course, can be expressed like this. Now, we have we want to work in Born-Infeld, so we have the constitutive relation, the one that I've given before. And we know that this expression here, which is the Gauss law, in Born-Infeld is the same, but instead of for the field E, we have it for the field D. Therefore, we must plug this here inside this equation. And we obtain that, okay, we can write first the field D in terms of the potential phi, and then plugging it inside the Gauss law. What we have is that this is the equation of motion for our potential. Now, just for the sake of completeness, this minus here appears because for simplicity we took as a charge electron, and we have taken Q, the value of the charge, positive. So with respect to this equation here, we have a minus being added to the left hand side. Of course, when we say phi here, we mean the complete Born-Infeld field. But the complete Born-Infeld field can always be thought as a Maxwellian. It's Maxwellian part plus a correction. Also, we have that because Born-Infeld theory must go back to Maxwell 1 if B goes to infinity, the Maxwellian part of the field must be much bigger than the correction. And because of the requirement of Born-Infeld theory, we have that the field itself, the full field, must be much smaller than B squared, the B. So, from this expression here, we want to expand using the binomial series this denominator here. We use the binomial and obtain this expression. Because of this condition here, we don't need to worry about convergence because actually this thing here is always much more than 1.
So look, I'm just puzzled by this assumption. Just I want to understand. I would say that parameter, which the B parameter, which characterizes Born-Infeld, is somehow the critical value given by Schwinger.
No,
it's not that one.
No. The Schwinger parameter is actually it's not a hard parameter if in a certain way. One can go beyond Schwinger field.
Okay,
one cannot go beyond the B field.
Your B field is
it's an upper bound.
It's maybe above the Schwinger field. Okay,
It's
so
not,
I understand.
actually, it's not correlated with the
I
Schwinger.
see.
It has nothing to do with
I see what you
because the Schwinger field comes from the
Quantum
quantum correction.
Yeah.
It's in the quantum regime that we have a field above which the nonlinearities appear and under which the nonlinearities can be negligible.
So for you, B is a parameter that you are right, let us say, at the end to fix it from some experiment, okay?
Yes.
Now,
There are values,
okay,
experimental
there are
values,
already experimental values.
but the experimentalists are not agreeing with themselves.
Okay.
There are several values. It's order 10 to the 18th quadrant, more or less.
Yeah, which is not so far about the Schwinger. So that assumption that you make, let us say, that sort of linearization, you say that the full phi field is Maxwell plus a perturbation which comes from the nonlinearity. So that is true in general, or that is true only in the radiation region?
Sorry, can you repeat?
Yeah, that perturbation, that, I mean, you say you split your phi field into a Maxwellian part plus some.
No, that is valid everywhere.
It's valid everywhere, even not necessarily in the radiation region.
No.
Because of the B parameter, that is the reason you say?
Simply because you can always think the Born as a Born infinite theory is a correction to Maxwell. Like I said, if you send B to infinity, you must obtain Maxwell. If you had not an upper bound in the field, you should have Maxwell.
No, you see, because that's what puzzles me, because if you have pure Maxwell, your field is divergent in the origin. If you introduce Born infinite, you come to a finite value, the maximum field B. So, if you go from Maxwell to Born infinite, you are going from infinite to some finite value near the origin.
But the finite value is not B. That's the point.
Yeah, but you say that your perturbation, so you have Maxwell plus something which is finite. So this finite is basically the B value, is the maximum value of the field, you know?
No.
It's not.
No. It's not in the.
Why not? Because the value of the field in the origin is not exactly.
It's not B.
It's
No.
not B.
No.
B is a field parameter for you.
Exactly.
Okay, I can try to understand that. Okay, but I get this information. Thank you. Go ahead, sorry.
Bem, deixa eu.
Yeah?
Pro senhor.
Pega a carona aí, pega a carona aí.
Posso falar?
Ah, português fala?
Ele está falando, deixa eu ver se eu entendi o que o senhor perguntou. Que o senhor está falando que tem um termo mais uma correção.
Isso.
Aí o que eu entendi que ele disse foi, você pode sempre falar isso porque você pode zerar essa correção e voltar para Maxwell.
Isso.
Aí você está preocupado com o fator B, que ele está falando que é livre.
É.
E é por isso ser livre a gente pode dizer que essa correção é menor do que a gente se
Isso.
interessa.
É.
Por isso que a gente pode desprezar em primeira aproximação.
É.
Mas entre parênteses ele falou que acontece o que com essa expressão entre parênteses? Isso vai entender a 1? Eu não entendi direito isso.
He wants to know this expression between brackets. So if you have some limit on that, yes, it comes back to the Maxwellian value. This is what he's asking.
Well, this is the.
No.
Sorry.
The other piece.
Yeah, I understand. But let me first say that this, if we send B to infinity, we are basically the field is the Maxwell field, and this is the Maxwell field. This is the wave equation for the Maxwell field. This here goes like 1/B squared. So if you want to say to see the Maxwellian limit of this expression inside the bracket, you must send B to infinity, and this thing here vanishes. So you're left with 1, which is precisely what you already have in Maxwell. That's what I was trying to say.
Okay, thank you, Luca.
So now we expand the first field, and we obtain basically, we see that this expression here formally is given by an operator that acts on the composition of it, but the operator itself is a composition of a Maxwellian part, because this is simply Maxwellian part, plus a correction of this, all the rest. So formally, what do we have? We have an operator OM plus Q prime acting on the field that is split in phi naught plus var phi. Then, by definition, the Maxwellian operator applied to the Maxwellian field gives the delta. Therefore, we can expand this expression here, we obtain this one, and this term here cancels this term here, and we are left with this equation for the correction. Basically, what this is nothing more than the linearization of the theory. We know the zero order equation, and we want to compute the first order equation. Applying this method to the equation, to this equation here, we obtain this one here. And now all that is left to do is to expand the field here and to throw away everything that is not of first order. So basically, expanding this, we disregard everything that is little phi squared, and we obtain this equation here. Moreover, we have three terms here, but of these three terms, we have this term here and this term here that depends on the little phi, and this term here that depends only on the phi naught, so the Maxwellian field. Therefore, this is the limit term because of the relation between the little phi and phi naught. That's why we can simplify the equation to this form here, and opening it up, we reach this equation here. Just some algebra, we perform decision of variables, and we can write the. It's important to see that the measure is not affected by this change of variable, and therefore we can write the equation like this. And what does this equation say to us? Well, we see that we have a wave equation, essentially. The wave equation shows explicitly that our problem has an axial symmetry, because the only relevant component is present inside the equation. Also, the field, sorry, not the field, the source, instead of being the usual point-like source that lays on the word line, is as a field itself, so it spans over the entire space-time. And this will create a great deal of problem. This is what I already said. Another thing, one might think that here we lost the reminiscence of the fact that actually we are trying to compute the field of a particle that lays on a certain word line. But actually we didn't, because phi naught depends on the word line itself. So now we have linearized the theory, and we can apply the green function method, also because this is simply a mathematical equation. We can find the solution to this equation, even disregarding the physics that is behind the problem. So here we can, without a doubt, use green functions. And if we knew the green function associated with this equation, then we would simply convolute with the source and obtain the solution to the problem.
But aren't you assuming that the thing on the right is a field?
Which field on the right? This thing here?
This. And it's different because it extends itself.
Yes.
And
this is not an assumption, this is actually what... what
and now you are relating it to a mathematical equation that deals with deltas and reduction to a
No. I say, if you want to solve this equation here, what do? You take the source and you convolute it with the green function for this operator.
Yeah, but when you say the source and you say convolute, and you're looking at this as a mathematical object, you're kind of disrelating this with the interpretation that this is an extended thing.
Yes.
And so that's a kind of you're solving the equation by ignoring a conceptual thing that's making the equation work. Because, as you said, it's how it works. It works as extended.
When I convolute it as a field.
Yeah.
I don't disregard the fact that this is a field. The fact that this is a field, you will see, makes that the convolution cannot be performed analytically. But nothing prevents me to convolute a green function in the field. But from a mathematical point of view, if you want to speak mathematics, I can take a field, I can convolute with a green function. I'm not neglecting it.
Yeah.
So, luckily, we are lucky because the green function for this equation is actually being calculated. In fact, I hope that you don't see because it's underneath here. In this paper, if you want, I can give you the reference. It is shown that in the regular spacetime, the wave equation for the Maxwellian field for a point particle is given by this equation. If you inspect this equation, it's actually the same to here. Therefore, but for a change of values, of course. And the solution has been found like this. But for the same reason, because this equation here gives the potential in the regular spacetime for Maxwell, apart from a numerical factor, we also have that this equation here is the phi naught. From this phi naught here, we can compute the source through this and obtain the field, which is like this. In fact, being a field, it depends on all our on the position. Okay. So, to solve the problem, we must simply, and I'm very ironical, solve this integral here. Unfortunately, like I was saying, the fact that this thing here is not a point like charge, not a point like source, but as a field, makes this integration analytically impossible, because instead of having only one divergence, which is the physical divergence on the word line, we have two divergences, one at the point where the particle is, and one that comes from the field that is divergent each time that I choose a value for my dummy variables in the integration. The field will always be divergent at that same line. That is the same line. Actually, we have tried to do it analytically, because this expression here can be somewhat related to hypergeometrical function, but unfortunately, in mathematics, it lacks a current structure for hypergeometrical function, and we could not make anything out of it. So we simply decided to go for the computational path. But instead of writing down a program that computes the integral, we have chosen to develop this denominator, perform the multiplication between the two series and integrate term by term. Because actually, if we perform this series development, we simply a series of power here. And the computer can integrate a series of power rather easily. So actually what we need to do from a computational point of view now is to find what is the numerical infinity for the computer, meaning that we need to find a certain value for the integration window above which enlarging the window doesn't change the integral, the value of the integral within the numerical accuracy of the computer. Also, we need to prove, and this is not something given actually, that the series this integral converges, because we need to say that after a big n, let's assume a big n in the series development, we must show that within our numerical accuracy, the n plus 1 term does not give a significant contribution to the Anyway, as I said, this is still a work in progress. This is how we intend to. But if we manage to do this, actually, the path is straightforward because actually, then it's simply a matter of computation of some program. So, some conclusion. I hope that I stress that even if there are strong constraints about regarding Maxwell electromagnetism, there is still room for nonlinear theory, to investigate nonlinear theories. We have tried to give a couple examples in the astrophysical context to show that we can investigate nonlinear theories in the statistical context. Like a toy model, we took an Heisenberg dipole involving the overcritical field and investigated the redshift, and we obtained that the redshift is actually comparable with that of degradation 1 for one metric and a couple of magnitudes more for polarization. We have a maximum at the equator for the first polarization and a maximum at the pole for the second one. One is a redshift, one is a blue shift. Then we tackle the problem of the unaccelerated particle in Born field, and we have managed to reduce it now to purely computational problem. Thank you for your attention.
Thank you to you. Pessoal, se vocês quiserem fazer perguntas aí, tal.
Questions?
Questions, perguntas. Comments.
To learn from you, how nonlinear electromagnetism competes with Maxwell equations, for instance, in astrophysics or in these two new experiments. And how, let's say, because we read physics in what you write. So if you were just write down Maxwell equations, you think that all the electromagnetism is moving in Maxwell equations. But then you have some points in astrophysics or in another subjects that say no. Here we could have clearly.
If I interpret correctly your question, you're trying to say, is there a definite experiment that can pinpoint the answer? Is electromagnetism Maxwellian or not Maxwellian? That is the question. That's partially what I said before to Professor Layer. The problem is that